Thank you very much, Augusto. Thank you very much, Kaylee. Yeah, so first, I just wanted to say that this presentation discusses some results from several recent articles. So these are those articles. And also, I wanted to say that in this presentation, we are going to discuss the problem of feedback stabilization. So we want to construct feedback stabilization strategies. And this problem is also related to the construction of control Lyapunov functions. And in fact, control Lyapunov functions are an extension of classical Lyapunov functions to control problems. We will discuss them in more detail a little bit later. And also, we are going to discuss the related problem of attenuating the curse of dimensionality. And I also wanted to say that this research was inspired by several studies in related fields, and these studies include the paper of Camille Grune and Weird on the characterization of control Lyapunov functions via optimal control and Hamilton-Jacobi equations. Regarding the curse of dimensionality, we were inspired by the works of Osher, Darbon, and also several other people from their research groups. And also, it was pretty useful for us to look at certain approaches related to the construction of sparse grids and interpolation on such grids. Can you hear me? Hello?
Like it's cutting, but I can hear you.
Okay, thank you so much. Yeah. First, let us start with some theoretical discussions. So what a control Lyapunov function actually is. So consider a general nonlinear control system described by ordinary differential equations. We have an initial condition. We have the set of our open loop control strategies. And based on the classical definition of Lyapunov functions, a control Lyapunov function is a continuous, proper, positive definite function which satisfies the so-called infinitesimal decrease condition. What does this condition basically mean? It means that at each state there is a control such that our function would decrease along the trajectories of our system. Also, control Lyapunov functions may be non-smooth. So instead of writing just an ordinary gradient, we have to include the Dini derivative, which is an extension of the concept of directional derivatives. So this is the definition of control Lyapunov function. And there is a general theorem, though it's based on quite restricted assumptions. And it says that if there exists a control Lyapunov functions, then there in principle exists an optimal feedback stabilizer. And in the work of Camille Grune and Weird, control Lyapunov functions, or CLFs in short, were characterized as value functions of appropriate infinite horizon optimal control problems. And one of our works tried to extend the theoretical arguments of this work and to develop a curse-of-dimensionality-free approach to feedback stabilization. The first issue was that the characterization of Camille Grune and Weird was based on infinite horizon optimal control, which is not very useful from the practical point of view. So when we want to compute optimal control strategies, we have to bound our time horizon somehow. And we found several ways how this can be done. Also, when we talk about Hamilton-Jacobi equations, we have to take into account that this is a partial differential equation. And if the state space of our problem is relatively high, even if it's greater than 3, we may face certain issues. For example, if our state space dimension is 4-dimensional, then our grid would be very, very large. And to achieve a desired accuracy, we actually have to take a very, very dense grid. And it would basically be almost impossible to handle this even if we use a supercomputer. And also, of course, the computational time will exponentially increase with the increase of the state space dimension. So this issue was termed as the curse of dimensionality. And it's related to the fact that there are certain relations between the values of our function and the related differences at one node and also at neighboring nodes. And there are several directions of how the curse of dimensionality can in principle be overcome. So let me briefly mention the possible approaches for that. First, I have to mention Max Plus and idempotent analysis tools. So they were basically applied to the problems where the Hamiltonian can be represented as the maximum or minimum of a finite number of elementary Hamiltonians that are related to linear quadratic optimal control problems. So that was one direction. And though the domain of applicability of all of such curse-of-dimensionality-free methods is in general quite narrow, the computational cost can be actually made polynomial with respect to the space dimension. Another direction is related to the reduction of regional infinite dimensional optimization problems to certain finite dimensional nonlinear programming problems for any selected state. So basically we can use the method of characteristics or direct collocation so as to reduce the problem of computing our value function or our control at a certain state to a certain nonlinear programming problem. And that is why each state can be treated independently from all other states. But even if we overcome the curse of dimensionality, the so-called curse of complexity may still be present. The curse of complexity means that even if we can treat states independently, these problems can be very, very complicated. And also there appears a problem if we have a limited number of states where we know everything, how can we combine this data to get a global approximation, especially in high dimensions? So we can use sparse grids. So we will discuss those things. So this was just a brief introduction. So first, let us return to our stabilization problem. Can you hear me?
Yes, it's going very well.
Yeah. So let me just briefly list some theoretical assumptions. So first we will do some theory, and then I will show some applications and numerical simulation results. So these are basic conditions that are imposed on our system. So F is the right-hand side. So it's locally Lipschitz with respect to X. Also, I have to say that many works require that the Lipschitz condition was imposed in the whole Rn. But in principle, for certain systems, we may have a so-called strongly invariant domain, which means that if we start in this domain, we will never leave it. And sometimes for many systems, all of our conditions may not be satisfied in the whole n-dimensional real vector space, but they can be satisfied in a certain strongly invariant domain. So it may be bounded or unbounded, but it may be such that everything is satisfied there. Also, we want to exclude any blows up, any solutions blowing up. So we impose a so-called forward completeness property. Also, our aim is to construct a global feedback stabilizer. But first, we have to ensure that there is a local stabilizer. So we suppose that there are feedback stabilization strategies that work locally. So starting from a certain sufficiently small neighborhood of the origin, there exists a control strategy that steers our system asymptotically to the origin. And there are two types of such conditions. The first one doesn't require the control to be approaching zero. And the second one requires that the control should also approach zero when our trajectory approaches zero. Also, we want to reduce a stabilization problem to an optimal control problem. So if we deal with an optimal control problem, we have to specify our objective function. So we will deal with the Lagrange type cost, which is actually the integral of some function g of x and u. And this function g of x and u also has to satisfy certain assumptions. So they basically look quite scary, but they aren't very difficult. They are quite standard, and they can be verified, actually. So if you, for example, look at the last assumption, so this basically means that if the right-hand side of our system f of xu doesn't grow as norm of x squared, if it's basically dominated by the square of the Euclidean norm, and if g of xu is quadratic, then this would hold for sufficiently large norms of our state. So it's not a very restrictive assumption, actually. So this is how the cost is specified in the work of Camille, Grune, and Wirth. So as I already told, originally the problem was stated as an infinite horizon problem. So you can see that there is plus infinity. And of course, if our system cannot be stabilized for certain initial conditions, this would be plus infinity. So to exclude these infinite values, we just want to use the so-called Khrushchev transform. So when v is plus infinity, it would be 1. So we don't deal with infinite values. And this regularization is quite useful. So when small v of x0, the Khrushchev transformed value function is 1, it's impossible to stabilize our system starting from this initial condition. And Camille, Grune, and Wirth could establish that under certain conditions, some of them are the same as I listed on the previous slides. This value function is a control Lyapunov function in the whole D0. D0 is the domain of asymptotic null-controllability, which is the set of all states from which our system can be asymptotically steered to the origin. But from the practical point of view, how can we deal with this plus infinity? It should be bounded somehow. So there are actually several approaches on how this can be done. So first, suppose that we don't know any local control Lyapunov functions. Then we will deal the case. Then we will deal with the case when we know a local control Lyapunov function. So first, suppose that our system is quite complicated and we don't know a control Lyapunov function in some neighborhood of the origin. Then what can we do? We can actually take a certain sufficiently small ball with respect, small ball with the center at the origin of radius delta, and we can state the problem of reaching this ball so that this functional is minimized. And now this is an exit time problem. So the time horizon is not fixed. Also, the time of reaching this ball is unknown. We have to find it in this optimization problem, but it's not infinite. So this can be treated numerically. And in our works, we have shown that when delta tends to 0, the functions v delta, which correspond to that exit time optimal control problem, uniformly tend to the original control Lyapunov function. So we could show these results. And also, if we use Pendragon's principle, which gives us necessary optimality conditions for open loop controls, we can actually characterize those approximations v delta via the characteristics, states and co-states governed by the system of Pendragon's principle. So we can actually reduce our infinite dimensional optimal control problem to an nonlinear programming problem stated with respect to the system of ordinary differential equations. So here we will actually optimize with respect to the initial co-state P0. And this is already a finite dimensional optimization problem. So by using this approach, we approximate the value function independently at different initial states. So what can we actually do? We can, if we are offline, we can just take a certain set of initial conditions. We can treat them independently via parallel computations. So then we get this data on those nodes. And then if we are trying to stabilize something online, we will interpolate the data and we will actually be able to get an estimate of our optimal feedback stabilizer at any state. We will also talk about the accuracy of such interpolation estimates a little bit later. Also, I have to say that if we work with characteristics, if we work with this system, it may actually be quite unstable with respect to the initial condition. If we can find an appropriate P0, then yes, it's very accurate and very good. But sometimes we don't know how to find an appropriate initial guess. So in this case, we can use so-called direct optimal control solvers. Direct means that we don't use any Pendragon's principle. So we just discretize it and we solve it. And it turns out that direct solvers are much more robust. They may be less accurate, but they are more robust. And also a very good advancement, recent advancement, that direct solvers can also give us estimates for those P0s. They are quite empirical. We don't know in general when they're going to work or not, but still, in certain cases, they are very good. Sorry. Yes, there is something. Yeah, so there is some delay because there are some pictures. This is just one example where we draw some sections of the value function in the stabilization problem for a 5-dimensional non-holonomic Brocket integrator. So this is a classical system. Originally, it was written in 3 dimensions. So if we take the first 3 equations, this is called the Brocket integrator. We also added 2 more variables, and we can actually approximate the value function and the corresponding control at any selected state. Also, this system is quite weird. You know, if you try to use model predictive control, so you just take certain sampling time instance, you approximate your control at this instance, and then you use a piecewise constant controller for stabilizing your system, there may be some traps. So the fact that this integrator is non-holonomic, and also you see that you have x times u, so the intensity of your control depends on the magnitude of your x. So in such cases, there may be some traps. So if you use piecewise constant controls, even if you take many sampling instances, you can fall into such traps. And now let us discuss the case when we know a local control Lyapunov function. So suppose that in general we consider a nonlinear system, but we can linearize it. So in a small neighborhood of the origin, we can approximate our nonlinear system by a linear system. And suppose that, and this is generally the case, then if the linear system is stabilizable to the origin, then we can actually use linear quadratic optimal control and Riccati matrix equation framework to find a control Lyapunov function for our linearized system. And it turns out that if we apply this control Lyapunov function to the original nonlinear system, it may also work. It wouldn't work globally, but there will be some neighborhood and some sublevel set of this function for which the infinitesimal decrease condition would work for the nonlinear system. So we can find a certain sublevel set of our local control Lyapunov function V local, such that inside this set, we denoted by omega C. C is the level. It works. So then our problem is first to reach this sublevel set, and then if we are inside this set, we can actually switch to our local stabilizer related to VLocal. And we won't leave this set if we are inside it, since it's a sublevel set, and the decrease condition for VLocal holds. So once we are inside it, we won't leave it if there are no disturbances. But in general, there may be some issues related to the fact that there may be some tangency. And we just wanted to find certain sufficient conditions for the absence of such tangencies. And though it seems rather obvious, it still has to be proved that under a number of assumptions that also aren't very restrictive, they are quite common and reasonable. If we concatenate this local control Lyapunov function VLocal and the value function in the exit time optimal control problem stated with respect to this target set, then this concatenation will actually give us the global control Lyapunov function. And once we have this characterization, we can provide a similar theoretical analysis for this problem. And it's similar to what we did previously for the problem where we don't know any local control Lyapunov function. Let me show one numerical example. So first I'll show the numerical simulation results, and then I'll discuss what was actually done there in terms of the numerical implementation. So this is also a classical system, planar vertical takeoff and landing aircraft. So X1 and X3 are basically the coordinates of the center of mass of the aircraft. X2 and X4 are the related velocities, the rates of change of these coordinates. X5 is this angle. X6 is the rate of change of this angle. Also, U1 is such that 1 plus U1 is the thrust. U2 is the rolling moment, and there is also the so-called coupling coefficient, which appears here. It shows us the relation between the rolling moment and the rates of change of the coordinates of the center of mass. also one is the normalized gravitational acceleration. And why do we take 1 plus u1? We just want our system to be resting at the origin when u1 and u2 are equal to 0. So that's just a very useful change of variables. So we take 1 plus u1 instead of just u1. In this problem, we can obtain the local control Lyapunov function via linearization. So it turns out that the system is locally controllable to 0. There are certain sufficient conditions for that. Also, we can construct the corresponding quadratic local control Lyapunov function. And then when we know this control Lyapunov function, we can take its sublevel set where the infinitesimal decrease condition holds for the original nonlinear system. So we take this as a target set, and then we state the optimal control problem outside the set with the corresponding target set. Also, we used certain high-dimensional interpolation techniques for the design of global strategies. And also, we know that for such classical under-actuated mechanical systems, there are some analytical feedback control laws. One of them was designed by Fantoni. It was also tested on a real aircraft prototype, so it's analytical. So there are certain analytical expressions that give us the control. Also, those analytical controllers are not constrained. So these are just some expressions. And of course, if we have certain constraints on the magnitude of our controls, they may not be satisfied if we are sufficiently far away from the origin. For analytical controls, yes, they can be implemented very easily. We don't have to compute anything. We just have those analytical expressions and we can evaluate them very fast. But we can see that, so these analytical expressions are, the corresponding trajectories are drawn in gray. So the dashed gray is the original analytical control of Fantoni. The ordinary gray lines are the same controllers, but we just use their saturated versions based on our control constraints. And we see that they work, but if we don't have any noise, if sigma is 0, sigma is just the intensity of some stochastic noise that we add to our system to test the robustness. So yes, they work, but still we the amplitude is quite large, so we move far away from the origin, and such deflection may be very, very dangerous for our aircraft. So it may reach such a deflection for which our model won't be valid. But if we add some noise, then we see that actually it doesn't work very well. So this is actually the variance, and we see that the variance is quite large. And this is actually for the system with noise, we consider the mean value of the norm of our state. But when we use model predictive control approach based on our optimization algorithm, we see that it's stabilized pretty well. And the variance is also not very large. But we have to know that our controller is based on optimization. And we have to compute a lot for any state where we want to do measurements. We have to solve a quite complicated optimal control problem. Yes, we can reduce it to a finite dimensional problem, but still this finite dimensional optimization can be very, very complicated. So even on powerful machines, it can take several seconds to handle this. But suppose that the dynamics of our system is very, very fast. Then the delay will be so large that that the controls we compute may already become irrelevant after several seconds. So in a real-time implementation, we sometimes cannot recompute the control by solving the whole optimization problem. So we can just try to make this online computation faster, though it may be less accurate. If we first try to generate some data offline, and then if we interpolate with respect to this offline data, and if this online interpolation is very fast, then we're good. Also, if we do interpolation, we know that we may require less sample points if we try to incorporate the gradient information. And it's good that our approaches for estimating the value function, control, and costate at any selected state also give us the costate. So the costate is actually you can see that it's P. P is the costate, or it's also called the adjoint function. And the costate actually represents the gradient of our value function. Of course, it's the gradient at the points where the value function is smooth, but we know that the value function is locally Lipschitz continuous, so by Rademacher's theorem, it will be differentiable almost everywhere. So almost everywhere with respect to Lebesgue measure, P will give us the gradient. So we know this gradient. If we know this gradient, we can incorporate it. And that's why we can use the methods of interpolation on scattered data that can use the gradient information. So there are several methods of this kind. So let me just list some of these methods. This may be inverse distant weighting. It's also called Shepard method. Also, for our simulations, we have modified it to have the proper values and gradients for our estimates on that level set of the local control Lyapunov function. And also, our modification works only if the local control Lyapunov function is quadratic. But if we use linearization for the construction of local control Lyapunov function, it will indeed be quadratic. Also, we can use radial basis functions. This is actually an extension of inverse distant weighting. Also, we can use kriging, which is very powerful. It takes quite much time to generate the data for kriging, but it's really very powerful, and also support vector regression. So in our simulations, we tested only inverse distant weighting and kriging. So what can we do? First, we have to specify the original set of sparse grid nodes. It's known that for interpolation scattered data, it's better to take a quasi-Monte Carlo sampling. It's different from the original Monte Carlo sampling in the sense that the distribution is not uniform, but we try to allocate our points as dense as possible. So, and it turns out that in many cases, it's much more accurate than using just ordinary Monte Carlo. Then we can first take our original set, we can generate the data there by treating each of these nodes independently and solving the optimization problems that were discussed above. And then we try to see how good is this approximation in terms of stabilization. So we just consider that this is some control Lyapunov function, and we want to test it where the decrease condition for this function is satisfied. Then at each iteration of our process, we have to find the minimum level of our approximation, the minimum level, such that the decrease condition for it is satisfied everywhere inside this level. And the new sparse grid node is placed at the solution of this problem. And this allows for successive improvement of the conservative estimate. So we just try to expand the sublevel set where everything is okay. And this is done offline. So we do this offline. Then if after a certain number of iterations, our sublevel set becomes large enough, then we can say that if we are online and if we start inside this sublevel set, and if the disturbances aren't very large, and if we don't leave this sublevel set, then our approximate controller, which is based on interpolation, which is much faster than the controller where we recompute everything, then it will actually steer our system asymptotically to the origin. Also, we have to know that this estimate is conservative. So in real life, the actual domain of attraction may be wider. And also, so here we just looked at certain classical examples. They are mainly used for some tests. But let me also point out certain more complicated applications where such approaches may be very useful and where we did also some things. So it's also quite interesting for me. So because at my university, I currently collaborate with biologists and microbiologists, and we recently applied for an NSF funding, and we just want to establish the so-called integrative biology Great Plains Research Institute. So it will involve North Dakota State University and also some other universities in North Midwest. And one of the directions of research is understanding of genetic variation. So we have some experimental data, some kinetic models from biochemistry that can show us how the bacterial growth regulation strategies work. We try to construct models based on certain optimality principles or maybe game equilibrium principles such that the corresponding optimal solutions or equilibria would actually resemble the experimental results. So we just want to understand certain general optimality or equilibrium principles that may be applied to such microbiological systems. And then we can also use them in biotechnology. So there were a couple of papers on that. So this is basically an optimal resource allocation problem for an E. coli bacteria. That's a quite common bacteria. It's used in theoretical science, also in biotechnology, and there is some trade-off. We can invest the available substrate resources either to protein synthesis, it's called gene expression machinery, or to metabolic machinery. This is a quite simple model. Of course, there are many other machineries, but first we focused on just trade-off between these two machineries. So there is a control strategy which shows us which part of the available resources we invest to gene expression machinery and to metabolic machinery. And there are also some other variables, but we basically focus on the two variables that show us how many proteins for gene expression machinery and metabolic machinery we currently have. And if we consider, yes, and of course we suppose that in the natural environment, our bacterial populations try to maximize their fitness, or it can be represented as maximal biomass accumulation. And it turns out that there are some certain optimal steady states that correspond to singular regimes. And the bacteria try to reach this optimal steady state in some optimal way. So we can state the corresponding optimal control problems, and if we don't include any noise, if we suppose that the strategy that our bacteria want to implement are implemented with no error, then it's quite interesting. You know, we arrive in chattering at chattering regimes. So chattering means that we have an infinite number of switchings at a finite time interval, and we can characterize the corresponding optimal feedback strategies. Of course, if we include additional variables, then we have to use our curse-of-dimensionality-free approaches and high-dimensional interpolation techniques. Also, we have to say that in such strategies with chattering, they aren't very realistic in the sense that chattering never happens in real life, but they can still serve as benchmark strategies against which actual control mechanisms can be compared. But also, if we consider stochastic optimal control problems, if we incorporate the fact that the strategies are implemented with some errors, then this switching surface will transform into certain domain, certain transition domain, which will be much more realistic, and it will actually be very it will actually be in a good agreement with some experimental data based on the kinetic model. So we see that, yes, and why this stabilization? Because we just want to reach a certain optimal steady state, which can actually be analytically characterized, or for more complicated systems, it can be numerically computed. So we have a certain optimal steady state, and we want to reach it so that certain functional is minimized. So this is optimal stabilization. So let me show also some results. And it turns out that our optimal feedback strategies are quite robust with respect to temperature. This is a very interesting result. Also, we can modify these models to consider biotechnological problems. So if our E. coli bacterial strains are genetically modified to be aimed at producing certain products of interest, such as glycerol, for example, then we won't directly control those mechanisms of bacterial growth, but we will regulate a certain inducer that may be based on specific chemical or light effects. So these chemical things or light will affect the bacterial strategy, and it can be regulated so as to maximize the product of interest. For this problem, it's more complicated. We haven't yet constructed any feedback, so we just consider it open loop controls, but I just wanted to say that it's quite promising to use the curse-of-dimensionality-free approaches for Hamilton-Jacobi Bellman equations as applied to such biological systems, even if they aren't very accurate. Even a certain suboptimal approximation may be very relevant. And also for this problem, there was a very good question. You know, there are two approaches to affect the bacterial control strategies. We can use either chemical approaches or light. You know, if we use a chemical approach, then our control can work only in one direction. So, for example, we can stop the growth, but then we won't be able to recover it. So it's very simple and it's not very expensive. So if you look at this graph, we actually see that first we basically don't do anything. So our bacterial population grows, it acquires certain resources, it also synthesizes proteins, and then we finally shut off the growth and we invest everything in metabolism. But we cannot come back. We also can use some light-based inducers, but light-based inducers are much more expensive and more complicated in implementation. And that was the question. So if we are in a batch reactor, so will sufficiently cheap chemical inducers give us good suboptimal results? So do we have to buy very expensive light inducers? And it turns out that if we use just a chemical inducer, we will be relatively close to our optimum. So at least for batch reactors, when we are in a closed container, so we don't add anything, so we just see what happens there. Then we just take everything and then we fill the container again, we close it, and then we do this successive batch reactor synthesis steps. So for such a situation, it turns out that mathematical modeling based on optimal control allows us to show that the cheap chemical inducers can show good results. And also, let me just quickly point out one more application. It's related to the stabilization of marine crane payload. So we haven't yet treated this problem, but it seems quite interesting because it's high dimensional. Also, these are vibrations. So here the problem is to lift a certain small boat or maybe some crane to a large ship and to stabilize the related vibrations. And also we don't want to hit our ship and we don't want to damage this load. And thank you very much for your attention. So this is the end of the presentation and I'll be happy to answer any of your questions. So.